So in this part, we are going to see an introduction to methods used in procedural animation, and in particular, we will start by something called particle systems. So we will see two things: how we can generate interesting trajectory for these particles, and also how to display them using an appearance of complex scene. So using particle system with procedural trajectory is actually one of the oldest methods that have been used in the early age of computer graphics. In the years 1980, most of the graphics were only static images. There were no method to generate advanced animation and very limited computational capability of the hardware. So here are two examples of such early models. So the first one is the explosion model for Star Trek II by William Reeves in 1983. And you can find a published research article describing how these explosions have been made. And the second on the right, in 1988, is an animation by Carl Sims, who was a scientist and artist who was one of the first to show such complex fluid-like animation. So the interest of particle systems is that they are lightweight in memory and in computation, as each element is very simple. And here is a basic example exercise of a particle system, where the particles, displayed as spheres, follow a free fall under gravity. So in this case, the geometric representation of each particle is a sphere. And the equation of motion is given by the parabola P of t is equals to 0.5 j times t squared plus v0t plus p0, where j is the gravity constant, v0 is the initial velocity, and p0 is the initial position. And we assume that for a given particle, it's locally created at time t is equals to 0. So to mimic such motion with an appearance of variability, we can use some parameters with random values for the initial position and velocity, limited lifetimes, and so on. And here is now a question for you. So can you guess the parameter values that we use for P0 and V0 in this example? So note that the coordinate system is such that X, Y, and Z is given by the respective red, green, and blue axes. So if you want, you can stop the video and think about it before pursuing, and we will discuss this question during the interactive session of the lecture. So now we have a bouncing motion. This will be actually the objective of your first exercise of the lab class. Now we can wonder what is the equation of motion of these spheres that take into account the bouncing. So the second question is how can you write P of t given the initial condition P0 and V0? So to help you think about it, you can consider a single particle emitted at time t is equals to 0. Then you can compute at which time ti the particle touches the ground. Then you can compute the new velocity after this impact. And by the way, how does this new velocity relate to V0? And once you have that, you should be able to express the complete equation of trajectory using a piecewise definition when t is lower than ti and greater than ti. And as a side note, you can also notice the short shadow effect of the sphere around the time of impact. And as a bonus, how do you think these shadows can be handled in the code? And this is another example. And in this case, the trajectory are defined using arbitrary motions, not necessarily related to physics. So here's another set of questions. So what are the parameters and the type of initial value that we need to attach to each particle? And it can be the initial position, the radius of the particle, which seems to be uniformly distributed between a small interval of values, but we may need other parameters as well. And the second question now is, what is the equation of motion of these particles? Note that implementing this example corresponds to the second exercise of the lab class. So far we only show results where the particles are displayed as sphere, but we can use small images instead. So in practice, it means that the particle is associated to a geometrical quadrangle. It's made by two triangles. And then we map an image as a texture on the quadrangle of the particle. So the texture can have a transparent background, and then the geometry of the quad is actually invisible. This allows to fake a complex geometry representation while using only very simple triangles. Also, the quadrangles can always face the camera. Then we call that a billboard. This is the case for the smoke-like effect. When you rotate the camera, you have the feeling of seeing a 3D smoke structure, but this is actually only the same image drawn on quads that always face you. And here you can see a single texture image of a cloud in the sunbay, and in this case the blue background is actually transparent. In addition, the texture itself can also be animated. In this case, we would call it sprites. And finally, the texture can also be modified depending on the point of view. In this case, we call that imposters, and then they give the feeling of the 3D geometry while being only 2D. So these billboards, sprites, imposters, they are actually very common in professional context, and in particular in video games. They can be used to model complex-looking vegetation and trees, while actually the complex leaves are only texture mapped on quadrangles. Sprites are typically used to give the look of fire, smoke, or even flows of water. So this will be the exercise of your lab class. So in this case, which kind of model should we implement to have this final result with the smoke? So to finish on this part, we will see a more complex example of usage in the case of visual effects. So here's an example of sequence of the Lord of the Rings. So let's first think about what element in this sequence is real or virtual, and how do we do these virtual parts. Obviously, the horse heads made of water are virtual effects. So the question is it made from a full 3D simulation of liquids? So this sequence is coming from the making of the movie to get an insight on how these productions are working. We can see several layers coming one after the other. First, we see the waterfall effect. This is actually a simple 2D video, and we can see that the flow is not going toward us, but it's a simple zoom in the video sequence. And second, we can see some head horses. Then we can wonder, why do we see these surfaces? So actually, these surfaces, they are used as starting point to emit some particles. And now we can see two layers of different type of particles. They are typically sprites with some texture of water droplets, and they fall and disappear a long time. And finally, when all the sequences are blended together, we get a nice animation of horse heads made of water. And here there is no real fluid simulation, it's only an accumulation of several simple layers that are carefully tuned. And this process is actually happening a lot in the special effect industry. So real 3D simulation would have been very costly and hard to set up, and possibly also hard to tune to get this unrealistic effect, such as these head horses. So tuning some effects using manual and procedural method is actually more effective in this case. And this is the full making of. At first we can see the real recorded scene. So this is the real river, much more quiet than the final shot. And then we can see some real recording of running horses that are the one escaping the water. And the other horses that are took in the water are fully virtually modeled and integrated into the scene. Next, we can see all the different layers of the water, and as we can see, there is a lot of layers to get this final plausible appearance. And finally, we see an overview of the sequence, and everything needs to be redone using this point of view. And we need to keep in mind that all of this work has to be done for a sequence that lasts about 3 seconds on screen. And I will finish this part with a few notes on implementation when dealing with particles in OpenGL. First, about the transparency effect. Actually, rendering transparent shape is not straightforward when using projection rasterization approach. And at the end, we need to use tricks. There is actually no perfect solution for it. So one possibility that offers OpenGL is to blend color for each pixel acting like layers drawn one after the other using the alpha channel of the RGBA color. But this color blending needs to be explicitly activated. So by default, the A component, the alpha component of the RGBA color, is not used. So to activate it, you can use the following code. So GL enable GL blend, that says that you will use color blending. And then you also need to set, at least once, the GL blend func with alpha 1 minus alpha. And after this, you can draw your transparent shape. And after your draw calls, it's safer to deactivate it to avoid its use on other shapes that you don't want to be transparent. So the gel blend func is a way to parameterize how the blending is computed. There is actually multiple possibilities that you can see in the OpenGL documentation. So to give various effects of layers like min, max, and so on. But for transparency effect, we use these parameters that basically state that the new color on screen is given by alpha times the current color, plus 1 minus alpha times the previous color that was already there. And now there is a few important notes with transparency. So first, the order of the draw call does count. So there is a previous color and a current color now. And the corollary is that we cannot rely on the use of depth buffer algorithm to handle transparency object. So depth buffer allows us to display opaque shape without having to care of the draw order, but in this case we cannot use it. And here is a summary of the general algorithm you can follow to work with transparent shapes. First, you draw all non-transparent objects using the standard depth buffer approach. Then you can activate the color blending and deactivate the writing into the depth buffer. Before drawing the transparent shape, you need to pre-sort them with respect to their depth to the camera. And as a reminder, you can compute the depth of a point relative to the camera in multiplying the coordinate of the point with the projection and model view matrices. And then get the z coordinate after normalization. And finally, you can display the transparent objects from furthest to the closest to get them in the correct order. So if you forget some of these steps, you may see some visual artifacts that are not always obvious to detect. So on the left, you have an example where the shapes are not sorted and the depth buffer write is still activated. So in this case, the red window is drawn before the blue one, and the bird is drawn before the grass. Then we can see that when this window and bird are in front, they hide the other shape, as the quad is displayed first, and the depth buffer is updated with values that are close to the camera, so the other image is not displayed beside. And a more subtle effect is obtained when the depth buffer write is deactivated, but the shapes are not sorted. It looks fine in some situations, but odds in others. As there is no sorting, the bird, which is displayed before the grass, is always displayed as if it was beside the grass, even when it's close to the camera, which leads to some odd appearance. So the effect is more subtle on the window, but the blue window is always displayed as if it was in front. So its black border, for instance, are never filtered by the red color. And as this effect is subtle, sometimes it can be okay to use it like that. Typically when we are working with blurry sprites, like smoke effects, when the element order are hard to distinguish from one to another. In this case, it avoids to sort the particle at every frame, as the cost of such sorting is not neglectable. Finally, there is another possibility that can be used for shapes that are not semi-transparent. So for each pixel, it's either fully opaque or fully transparent, which is often the case for the impostors. In this case, we can use the command discard on fragments that are transparent. So in OpenGL, discard used in a fragment shader stops its execution. So there is no color output and no write in the depth buffer. So it mimics the total transparency at the pixel level. The code to be added in the fragment shader is very simple. If the alpha component is less than some threshold, typically around 0.6, then we discard the fragment. So this approach has the advantage of being very generic, and it's fully compatible with the standard pipeline at the pixel level. So using discard, we don't have to sort the shape by depth, and the standard depth buffer algorithm works at the pixel level. We can draw the shape in any order we want, and we don't need to worry if it's transparent or not. So this is typically the type of approach used for imposters with complex geometries like trees and so on. So on the downside, as it's a binary approach, we can see some aliasing artifacts at the border of the fragments that are discarded. And of course, this approach doesn't work for semi-transparent objects, for which we need to use the color blending in the correct order. And now a few words about another concept called instancing. When we deal with particles, we typically need to display lots of similar shapes. If we have thousands of particles and call each of them individually, it quickly starts to be costly and slows down the rendering. So the issue here is that we have a large number of draw calls, for instance, GL draw elements in OpenGL. A draw call does have some cost and it forces the synchronization between the CPU and the GPU. So we should avoid having too many draw calls in a single frame. So this case is shown by the typical loop where we iterate over all the particles, apply some operation for the given index k, like set the position for instance, and then call the drawing of the particle. In this case, we have as many draw calls than particles. So a solution to avoid having too many draw calls while keeping large number of particles is to use instancing. Instancing simply means that OpenGL will make the GPU draw many times the same object using a single call. Its basic use is very simple. Instead of calling GLDrawArray or GLDrawElement, OpenGL provides the function GLDrawArrayInstanced and GLDrawElementInstanced. Then in the C++ code, we only have one call to drawInstanced, and the last parameter is the number of instances to be displayed. Now in the shader, we have the built-in variable GLInstanceID that contains the index of the current object, so it's the same than the parameter k in the loop. And of course, if we have some operation done using the index of the particle, it now needs to be computed in the shader directly. Using instancing in principle is very simple. It just moves the loop inside the GPU in a way, and this allows to use the full computational capability of the GPU without losing time with synchronization between CPU and GPU for a large number of objects. However, if you have complex operations to do for each particle, these are to be done in a specific shader when possible. And finally, here's a comparison between using multiple draw calls on the left and using instancing on the right when displaying spheres. With multiple draw calls, we can increase the number of particles up to 15,000, and then the FPS starts to be quite slow. It means that we only display 750,000 triangles. When using instancing, we can display way more objects in real time. With the GPU used for the recording here, it goes up to almost 500,000 of particles, while still remaining at 60 frames per second. And in this case, it means that approximately 22 million of vertices are displayed. But of course, this timing may vary depending on your graphics card.